All right, let's start the last of the 4 talks. Thank you very much for coming. What did we do so far? Well, in the first talk I gave an overview. In the second talk I introduced Brecht-Tietz theory and the multi-passat filtration. In the third talk we talked about representations of p-adic group. We proved how to construct depth zero supercuspal representations. And we started talking about JKU's construction of essentially all supercuspal representations. So all supercuspal representations if P doesn't divide the order of the Weyl group. Maybe I should also say, our notation always is F is a non-Archimedean local field, so finite extension of the p-adic numbers or of the Laurent series or a finite field. And G was always denoting a connected reductive group over the field F, and we assume that it's tame throughout. Sorry, that was our notation throughout this lecture series. Well, tameness we assumed only now. And I promised you to say a bit more about the construction of supercuspal representations, so I just wrote down once more the input that I introduced last time. So the input was this sequence of twisted Levy subgroups, so a sequence of subgroups that becomes Levy subgroups over some field extension. A point in the Brecht-Tietz building, or I should have also said an important is that the center of the smallest one is anisotropic, so compact modulo the center of the largest one, or that's just a G here. We take a point in the smallest Brecht-Tietz building that is a vertex there, and we embed all these Brecht-Tietz building in the larger ones. That's given to us, the embedding in that case. We took a bunch of real numbers. What are the real numbers? These were just the depths of a bunch of characters. One character for each of the group, or each of the group except for the last one. And these characters, they should be generic. So last time we discussed what generic meant. And then we also took a depth zero input, which was a representation of this subgroup of G0 that is fixing, stabilizing a point, this point X in the building of G0. And this was chosen in such a way that it gives rise to a depth zero representation of the smallest group G0. In other words, it's trivial on the 0 plus subgroup, and on the depth zero subgroup, it's a sum of cuspal representations of this quotient, which we saw was a reductive group over a finite field. And so then also, just recall, we had the construction. The construction we already talked about a la JKU, or a twisted version of JKU, was that we associated to it a compact open subgroup, which was just, we took this smallest group here where the depth zero representation lies, and for all the other groups we took the Ri over 2 pieces to the last one, and minus 1 over 2. And so we have already seen last time that on each of these groups, GI, we were constructing representations by extending the character to this piece and then inducing up. And on this depth zero, on this E0, we were constructing depth zero representation by inducing up the depth zero piece. And now we just have to put everything together for this larger compact open subgroup that's made out of all pieces. And then we also said that, I gave it already away, that rho tilde, so let me put the definition dots here, was defined to be rho 0 tensor sum representation kappa. And I said I will tell you more about kappa this time. So now that's what I want to do. Tell you about the construction of kappa. And to simplify things a bit, let me say for the case that n is equal to 1. So that we only have a one-step sequence, and afterwards I tell you how to do it in general. So that means, i.e., we only have a sequence G0 contained inside, and let me assume it's not equal to G1, and that's where we stop. So that's our G. And then what do we have? Well, we have the point X, and then we have the sequence of characters, which is, so let's say, i.e., the input is these two groups, the point X, a positive real number. Let me just call this R, because there's only one that shows up. The sequence of characters, now it's only one character, so let me just call this phi. Let me just drop all the indices, because I now restricted to the case that everything just shows up once. So that's the input. And now we want to construct something. So here's the construction. Well, first of all, let's recall what is k tilde in this case. K tilde in this case is just gx0, or g0x, better said, times g1, which is the same as g of depth r0/2, which I just called r. All right, now let's try to do the construction of kappa. So here's the first step. So we have already used the depth 0 part for the row 0. So I said this kappa, this is really built out of just the characters. So in this case, it's built out of the character phi. And so we just try to imitate what I've done last time when I constructed representations out of phi. And that's the first step. The first step is that we extend phi, let's say phi, actually just restricted to this group G0x, that's all we need, to a character of, well, we extend it to a character of as large as possible, the largest possible subgroup of k tilde, and it turns out we can extend it to a character of gx0 gxr/2 plus. And that's exactly the same as what we have done last time. So we extend this essentially by setting phi, and I put this maybe in quotes to be trivial on the root groups of G outside G0. So we just set it to be trivial everywhere on these r/2 plus pieces that are not already inside G0. And since the commutator of the r/2 plus piece lies in the depth r plus piece, so lies in the kernel of phi, this makes total sense. That's totally fine. And that's just what we have done last time. Last time we just had the simplifying assumption that the r/2 piece is the same as the r/2 plus piece here. So now we have to deal with this difference. And that's the rest of the construction. And let's give this character a name. Extend this to a character. Let's call this phi hat, because that's how JKU likes to call it. So here's the second step. And that's the, let me call this the step of the Heisenberg representation. And the second step is, well, we really want to get to the depth r/2. So we extend, well, it's not quite extend because we changed the dimension of the representation. Extend phi to a representation, a higher dimensional representation in general, to a representation of gx r/2. So we want to get to all of r/2. We can't quite get to all of gx0 anymore. We lose a bit, so we have to put this back in the third step. So how does this step go? So there are two nice facts. The first one is that, well, we want to use the theory of Heisenberg representations. What is the theory of the Heisenberg representation? That is that you start with the Heisenberg group, which is something attached to a symplectic vector space over a finite field. So we have to construct that first. And so where is our symplectic vector space lying? It's lying here. Fact, so let me not run into that. If we look at the space gx, so we want to construct something on gx r/2, and we already have something on g0. Well, since we just want to go to r/2, I mod out the r/2 please only, on the r/2 piece of g0, and we already have something on the r/2 plus piece of gx. So that's where our character lives, and that's the group we want to get to. And so that's really the difference that we care about. If I quotient out, let me call this v, maybe r/2. This actually, so first of all, this thing is commutative because the commutator of two elements in here has deeper depths, or in general, because last time we already saw that if we just mod out this quotient here, we get a vector, we get something isomorphic to a vector space over a finite field. So if we mod out even more, that's still a vector space over a finite field. So this is isomorphic to an f Q vector space last time we said, but let me actually just say an FP vector space. That's nothing surprising yet, because that's what we learned last time. I just view FQ as an FP vector space. But now it actually comes with a symplectic form with a non-degenerate symplectic form. So it's actually symplectic vector space. And what is this form? So the form, well, it's something where we take two elements, say G1 and G2 in our quotient, so let's say in this bigger group, and I have to define a symplectic form for you. And what do? Well, one thing I can do if I have two elements, I can take the commutator, G1, G2, G1 inverse, G2 inverse. What do we know about this commutator? Well, we know that the commutator lies in the smaller group here, because, well, this quotient is abelian. And what else do we know? We know that on the smaller group we have our character phi hat here. So we can then take this and apply our character phi hat to it. And ta-da-da-da, it turns out that this is actually a non-degenerate symplectic form. That's the fact. And so where does it actually come from? This non-degenerateness, that comes actually from the fact that this phi is generic, is G generic. So that's where we use the genericity. The genericity translates into this symplectic form being non-degenerate. All right, that's good. Maybe I should have also said this is really valued in the complex numbers, so secretly we identifying the p's root of unity inside the complex numbers with fp. That's something happening in the background. All right, that's great. So here's our symplectic vector space. And now then the second fact is, and that's just the theory of the Heisenberg representation. So that's just translated this theory into this setting, which says exactly what we want. It says there exists a unique, up to isomorphism for those who like to be pedantic about these things, there exists a unique, irreducible representation. Let's call this omega, the omega of this bigger group of Gx R over 2, such that if I take my representation and restrict this representation to the group Gx R over 2 plus times G0 x R over 2, that's where our character was defined. This is just given by our character, well, times the identity of this vector space. So there's a unique irreducible representation that is phi hat isotypic. Maybe some more information. This representation has dimension. We know exactly what the dimension is. The dimension is the square root of the number of elements in this finite vector space. Or in other words, it's p to the dimension of the vector space divided by 2. So this is a representation we understand rather well. It's just compactly induced from, I always miss this word, from a vector space of half the dimension. And that's the second step. So that's great. We now have a representation. Lagrangian was the word I was missing, so it's induced from a Lagrangian. So we now have a representation of this bigger group, but we really want to get to also have a representation of this group where we include all of the stabilizer of x inside G0. So that's the third step, and that's the step of so-called Weil representation, which is to extend the representation to an representation of the big group. So what we want here is want to construct an compatible action of gx0, sorry, on this representation omega v omega. So that's the last step, and that's done via wave. No, it's not the last step, it's the almost last step up to twist. That's via wave representation. So how does that go? So this group gx0, we already, well, we didn't quite say, it normalizes this, its filtration subgroup, it also normalizes this bigger group. So this group actually acts on, well, it doesn't normal, yeah, it normalizes this thing. So it acts on this quotient, gx over 2. Or maybe I should just say it, yeah. But I just wrote this as v r over 2. I could have saved some writing. Just via conjugation. And then you can check, just by this definition of the symplectic form here, that this is actually preserved. So if you just conjugate here everything by g, you see, by something in g0, if you conjugate everything here, you see it all cancels out except a big conjugation, and since it's a character, it's preserved. So that means this action preserves this symplectic form. In other words, what does it really mean? It really means that we get a map from gx0, from g0x, into the symplectic vectors, into the group of symplectic automorphisms, so in the group SP, the symplectic group attached to this vector space and this inner product over there. And now comes in the theory of the Weyl-Heisenberg, of the Weyl representation, which is just telling you that there is an action of the symplectic group on this representation omega. And that's just the Weyl representation. So that's what Weyl did. He constructed this representation. You can easily see by irreducibility that there is a representation that is a representation up to a scalar, and so one has to then check that all of that lifts. And one can do that. And that's the representation I want to take. So I want to now take this representation to extend omega to this whole group, except that actually I want to tensor the whole thing with phi. Because I need to put the phi back in, so I really want this group to also act via this character phi. And so then I call the resulting representation, of this group g0x times gx over 2 kappa non-twisted. That's my non-twisted kappa, which is built out of the Weyl-Heisenberg representation. And so that's what JKU did. That's what people worked with for a long time. I want to now add a small twist to it. That's step 4, which is that I want to set kappa to be equal to the untwisted representation times some epsilon twist, and I will not go into the details of what the epsilon is. I said last time it's something that comes only from the gx0 part that is trivial on the deeper depths, and it's a quadratic character. So that's a construction of kappa. Maybe one word in general. So in general, yeah, are there any questions? Maybe I should ask first. Are there any questions? In general, so for general U data, what we do is, let me get the indexing right. For each GI, where 1 is between I and n, we attach to it a kappa I in essentially the same way as we have done here, where I just took the one-step case to simplify things, and then we define kappa to be just the tensor product of all the kappa I. So that's the construction. Now we know, well, up to the fine print, to the details, how to construct this. I want to say a few words about how to show that this gives us supercustal representations, and then I want to construct types for you. So let me recall the theorem last time, I think it was theorem A, that said that if we now compactly induce from kappa tilde to G this representation rho tilde, then this is irreducible and hence supercuspidal. So let me sketch the proof. Proof sketch. Really just the sketch. Well, so I basically spent all of last time to give you an idea of how the proof could go. So how can we prove that something is supercuspidal? We prove that it's irreducible, then it's supercuspidal. How can we prove that something is irreducible? Last time we learned that we need to look at the space of intertwiners, and at the space of intertwiners we need to look at all the elements that intertwine something and show that these elements are contained in K tilde. So assume that G is an element that intertwines our representation rho tilde on K tilde. So intertwining, this meant that the Hom space of G K tilde intersected with K tilde of G rho tilde with rho tilde is non-trivial. And we need to show that, so need to prove that G is contained in K tilde to conclude. Then we are done. That's what we learned last time. So that's not the best. So how does the proof go? How do we show this? Well, there are two steps to the proof. The first step is show recursively that G is actually contained in K tilde G0 K tilde. So we reduce the problem to G0, and this is done using that the phi i's are generic. So more explicitly, here is the precise statement lemma in the case that n is just equal to the thing that I just erased, n is equal to 1, because it's easier for me to write it down in that case. So that's due to JKU. Suppose G intertwines just our character, just this phi hat restricted to Gx over 2 plus, nothing more. Then we can already conclude that G is contained in K tilde G0 K tilde, where in this specific case, K tilde is just Gx over 2. So we really just need the character to obtain this result. And how can we motivate this result? Well, last time I somehow told you what is generic. I motivated generic as being very similar to regular semi-simple. So it's basically as regular semi-simple as it can be inside inside G0. Inside G0, inside the center of G0, as regular semi-simple as it can be in the center of, well, roughly in the center of G0. So let's just say it's as regular semi-simple as it can be. And, well, what does it mean to intertwine a character? It somehow means it commutes with the character. And now, what are the elements that commute with something that is regular semi-simple? Well, this is just, for general regular semi-simple elements, it's the torus. But if you take something regular semi-simple in the center, it would be just the group itself. So it would be just G0. And that's roughly the motivation for why we need this character to be generic to make this conclusion. So Roughly intertwining means similar things to commuting with this element. Generic means similar to regular semi-simple, so the elements that commute are really just those elements in G0. Of course, the actual proof is a bit more complicated, and also I said it's regular semi-simple up to depth r/2. That's why you get the r/2 piece here. So that's a bit the motivation for that step. And then the second step is that, well, now we can, using the first step, we can assume that G lies inside G0. And now the way I actually concluded things is essentially, so JKU reduced it literally to G0 using a lot of work. And what I did is essentially I tried to upgrade the arguments we've seen last time for the depth 0 case. So I showed you last time how to prove that if we take a depth 0 input, how to show that the compact induction is irreducible. So that's more in Prasad's word. And now you can imitate the same, but, well, you have to take into account that this rho tilde is really rho 0 tensor kappa, so you have to work hard to make the kappa somehow go away. So assume, let me say, assume this now can use similar, well, much more difficult arguments to the depth 0 case using that this representation rho 0, v rho 0 is caspital when restricted. So by is caspital, I mean exactly the statement that it's a sum of caspital when you restrict it to gx0. And we have seen last time that that meant that if we are not stabilizing the point x but are somewhere else, then we got a contradiction to the representation being caspital because we got a unipotent radical that acted trivial of the finite group. Can use similar arguments to show that G is actually contained in G0x, so really fixes the point x. And that's then how we conclude. All right, so that's a quick sketch of how to prove that these are supercaspital representations. And that's the end of the supercaspidality story. Now I want to move on to types. Are there any questions so far about the construction? All right, then let's move on to types. Let's see, quick recall. We've seen the definition already last time, but I think it doesn't hurt to recall that K rho is called an M sigma type, where M is a Levy subgroup and sigma is a supercaspital representation of M. If and only if the following happens for all pi, for all irreducible representation pi, irreducible representation of G, we have that the following statements are equivalent. We have that pi is contained in the Bernstein block attached to this M and sigma, if and only if, or maybe I write this below, if and only if the representation rho that we have here restricted to K, well, it's the representation of K, embeds into pi, restricted to K. So the Hom space, K representations, is non-zero. So that's what a type was. Okay, now here's a compact subgroup. And we have seen in the first talk why this is so important, because it decomposes the whole category into blocks, into these Bernstein blocks, and we can understand each Bernstein block using the type. And we see that each Bernstein block, if there's a type, is equivalent to a category of modules over Hecke algebra. And that's what we do after the break in half an hour to understand the Hecke algebra. Now I first want to understand a bit better what are these types. So let me see, what do I want to do first? First, let me state a fact. A result of Bushner and Kutzko, who introduced the type theory in 1998 is when the paper got published. And that's the connection between supercuspitals and types. So we just constructed these supercuspidal representations from compact open subgroups. And during my first talk, I already said that if the group has a center that is finite, and if you have a supercuspidal representation induced from something, then this something is a type. Here's the more general statement of that. So let's say let K tilde be compact mod center. And rho tilde an irreducible representation of K tilde such that pi, say pi rho tilde, which is equal to the compact induction from K tilde to G of rho tilde, is an irreducible, hence supercuspidal representation. So that's the thing we have done so far, constructed supercuspidal representation in this way. So then how is this related to types? Then there is a type K rho, and I'll say in a moment what K rho is. K rho is an G pi rho tilde type for the following things. So what you want to do is you want to just say K rho tilde and rho tilde are a type, but K tilde is not compact a priori, it's only compact mod center. So what you do is take as K the maximal compact subgroup inside K tilde, and as rho you take an irreducible subrepresentation of the restriction of rho tilde to K. So that's the connection between our previous construction on types. So once we have a construction of supercuspidals, we also have a type for the corresponding Bernstein block. And the Bernstein block, this is rather nice and easy because, well, all of that it contains is irreducible representations is just the, well, I should maybe say nice and easy. It can be complicated, but not as complicated as the rest. All the irreducibles are just unramified twists of your supercuspidal representation. That's all you can do. Okay, so that's how to get between supercuspidals and types. Now, I want to construct for you the types following the Kim and Yu construction. So let's see, how do I do this? Maybe I write this already here. Types, oh no, I don't write it here, I write it up there. So I want to construct the types a la Kim and Yu. So construction of, instead of supercuspidal representations, I want to say construction of types. Oh, and I forgot to say something. I meant to say something very important, which is that P is not equal to 2. In all the construction of JKU, P is always different from 2. I forgot that last time as well, I'm sorry. So now I'm saying this once and for all. P today and for Yu's construction yesterday is different from 2. For the Weil-Heisenberg representation, that matters. I hope that we can remove this assumption eventually, but for now that's an assumption. So let's see, how can we construct types? And the idea by Kim and Yu is that we basically use almost the same input, but this input only gives us supercuspidal representation, so we need to relax things a bit. And so here's what we do. We take again a tame twisted Levy sequence, so a sequence of Levy subgroups that are the twisted Levy subgroups, but we remove the assumption that the center is anisotropic. That's what we remove here. Then we also take a point in the building of G0, but we remove the assumption that X is a vertex. Once we remove the assumption that X is a vertex, there is more structure to it. So now X is suddenly no longer a vertex, but from X, we obtain a group M0 that has the following properties. And now I need to So this is all supercusp representation. So let me erase that part. So from X, I get M0, a Levy subgroup of G0. And what is this M0? So M0 has the property that, so this continues here a bit for space burp. So such that the point X actually lies in the building of M0, which lies in the building of G0, and X inside the building of M0 is a vertex. So there exists a building for a Levy subgroup that contains X where it is a vertex. So that's the first part. And the second part is that we want that M0 X0 mod out by M0 X0 plus. Well, M0 X0 first of all embeds into GX0, 0. And then I can mod out here also the GX0 plus piece, and I want this to be an isomorphism. So this is an isomorphism. So I'm basically locally recovering all the information. Maybe now that I'm writing this on the board, maybe it would help to see an example. If G0 was SL2, so this is my building for SL2. If the point X was here, then M0 would be just the diagonal torus. No, that doesn't make sense. Well, that does make sense. Does it make sense? Yeah. That's not quite what I wanted, but okay. Well, the other option would be that, no, that's exactly what I wanted, sorry. That happens when you make up examples on the spot. So G0, the building of G0, in that case is this whole tree. And the building of M0 would be just the point, it's just the torus. The reduced building is just the point. And you can embed it so this would be then the building of the reduced building of M0. And you see that the quotient is exactly the correct thing, because if you take the quotient here, you get exactly the same as the quotient of the torus. And you also can see that locally the root system is really the root system for that group rather than the bigger group. So that's one levy that you get out of it. Out of that, you also get a bunch of other levies, because you can construct for each GI a levy MI, which is just defined to be the centralizer in GI of the maximal split torus inside the center of M0. And whoops, finally, of M0. So you take, let me say this again, this is the maximal split torus in the center of M0. So that's the center. And then you take the centralizer of that in GI, and thereby you get Levy subgroups inside G. And this now gives us a sequence of twisted Levy subgroups, M0 inside M1 and so on, which is actually the datum which can be used to construct supercuspidal representations. All right, so that's a bunch of data. Yet now you might wonder, why did I define all that? So you can actually, if you see this the first time, you can just forget about this. But the reason is that I need to write down one condition. So we remove this condition that X is a vertex, but instead I want to have the condition X satisfies the condition that it's generic. By generic, I mean basically almost all X are allowed except a few are excluded. And what I really mean is that, so we have constructed this M 0 in a way that we have this isomorphism here, and I want the same to hold for all the other groups. So I want that I take mi x ri minus 1 over 2 mod out by mi x ri minus 1 over 2 plus, that this is the same as doing the same for the GIs. Oops, the minus 1 is there. So this is just, why is this there? In the construction that I erased, we had this step where we needed to go from step Ri over 2 plus to Ri over 2. That's where we used the Heisenberg representation. And this assumption here basically says that everything that happens there is happening inside M and nothing happens outside M. So it's just saying that all the jumps for root groups that happen at depths Ri or I minus 1 if you normalize things, well, if you index things in that way, happen within inside M. Nothing happens outside M. So that it's just something technical, but that's just saying everything reduces really to M. M is the interesting thing. So that's what, so I should say for all I. For all I. That's what Julie Kim and JKU refer to as generic embeddings. There is a question. R0 is the first. I start with I equals to 1. I start with M1. M1 corresponds to R0. I'm using U's convention. My convention is that I corresponds to I, but different conventions. So you start with for the 0 group, we have already the condition over there. That's how M0 was defined. For M0, we have the condition here. And then for all the other groups, you take the corresponding depths and the corresponding. R0 you have. It's sorry. This is Ri minus 1. So it's M1 x R0 over 2 mod and so on. Yeah, sorry, I guess it got very small, yes. So it's just whichever R you need to. I usually in the past needed to always look it up. What is now the convention? But whatever shows up in the construction, that's really the thing that matters there. All right, so that's the point. So we relaxed everything. Basically, we relaxed all the conditions on the points. We just wanted it to be generic in that sense that really, it's generic in the sense that almost all choices satisfy this property. And as I said, Kim and Yu, they use the notion of generic embeddings to assure that by saying we embed the buildings of M in a generic way. There are many ways of saying the same thing. Yes? So the way I do it is that I basically fix my embeddings first, and then I view my point as something that lies in everything. Yeah. Here, I have to work with reduced buildings because that's what I set up, but usually I would work with the enlarged buildings, and then the images of the buildings of the levies are canonical, just the precise embedding is not canonical, but the image is canonical. So I take the embedding as given and then look at the point rather than fixing an embedding, which is what Kim and Yu do. So both ways work, yeah. Thanks. All right, so that's the, and maybe I should also say in the supercuspal case, the embeddings are actually canonical because there's no center. So that's, now I'm getting a bit into the trickier part of it. Well, the real numbers are the same as before. I already used them here. The characters, as before, we just take some generic characters of these depths Ri's. And, well, the last bit of information is the depth 0 piece, so I have to modify this slightly as well. So this rho 0 now is an irreducible representation of, instead of this group, I have to take a slightly smaller group. The group I need to take is gx0, just the x, 0 piece times m X0, and inside there just the compact subgroup. It's basically by the fact over there, which says that if you have a supercustom representation, we get a type by looking at the compact restriction, and that's the same thing here. For technical reasons, I need to use this decomposition. You'll see later why that's actually needed, why I need this group rather than just the compact subgroup of that. And let me maybe call this KX0 for later. But other than that, I do the same thing. So I have now this subgroup, this compact subgroup, and I take a representation on there that is trivial on GX0 plus, or that's what I want, and that restricted to GX0 is a sum of cuspidal representations of this GX0 quotient here, which is by the thing above the same as taking the quotient for the M0s. So it's really just relating everything back to M0. And so this last piece, let's see, orange worked also, I think. This last piece here, this piece here is actually a depth 0 type. So this KX0 together with this rho 0, this is also a type, and this is a type corresponding to a depth 0 representation. Or rather to a whole block consisting of depth 0 representations. So as before, in some sense, we take a depth 0 type, and then we take a bunch of characters to get a big type. So that's now is the input for the construction of types. So I might also call this sometimes Kim-U datum. Previously, we had the U datum, and now if we put all these yellow additions into it, basically relax a lot of conditions, then we get an input for types. And now from that, we can construct types. So here's the, oh, that's orange. The construction of types now, we need a compact open subgroup K. And that's essentially, again, what we did before. We need the depth 0 piece. The depth 0 piece is this thingy here, which I also call KX0. And then we need all the other pieces, so we take all the other pieces. GNX Rn minus 1 over 2. That's just my compact open subgroup, and then I construct my representation rho of that, and that's again like last time. This is just my rho 0 over there, which is defined on this first piece, times kappa. The kappa is constructed the same way as before, what I've just shown you. So the construction is really, really the same. And then theorem, this is a type. Theorem, I guess that's Kim and U. And my initial is that this K rho is a type. And it's type for some M and some sigma. It's an M sigma type. But I haven't really told you what M and sigma is. Well, I did kind of tell you what M is. M is just this M constructed here. M is just Mn. So that's how one can construct types. And, well, let me put my name fully there and also say that all types are of this form. And if P doesn't divide the order of the Rye group, then for every M sigma, there exists a type of that form. So an M sigma type of this form. So really all Bernstein blocks can be understood using this construction here. All right, so this might be a bit overwhelming. Why does this construction work? Why do we get types? So I want to use a few more minutes to actually tell you what is underlying this construction, why does the construction work, why can we essentially just take the construction of supercuspidals and weave it up to types. And then afterwards I'll tell you more about Hacker algebra so that we can actually use these types to understand the Bernstein blocks. So that's the theory of covers. Here is the definition. So what do we need for cover? So the input is, let's say, M inside G is a Levy subgroup. What else do we need? We need Km inside M and K inside G compact subgroups. Compact open subgroups. And we need rho and rho m, capital M, irreducible representations of Km and K, of K and Km respectively. And now I want to try to build a relation between them. So what I want to, maybe I should say this first, what I want to do is I want to take a type for M and get a type for G from it. And that's essentially what we can apply here then, where these M's that I've constructed, if you extract the data for these M's, you actually get a supercuspidal type. You can construct a supercuspidal out of it. And then the whole data for G should just give you something that is a cover that then gives you these construction of types. So I want to now try to connect types for M and types for G. So that's the input. M is the Levy. Then we have these Km and Ks with representations rho and rho M. And then we say the following. So we say that this K rho is a cover of Km rho M if the following hold for every, so if the following, let me say, let me call this a G cover to be precise. It's a G cover. If the following hold for every parabolic subgroup, P equals Mn inside G, and let me make this plural, and second parabolic subgroup P bar, which is equal to Mn bar, also a parabolic of G, with the intersection of P and P bar being M. With P intersected P bar equals M. In other words, I take any parabolic subgroup that contains M as the Levy subgroup and take an opposite parabolic subgroup, so it means one where the intersection is only M. And now I want things to decompose nicely. So if the following hold for every parabolic, well, it's not the nicest English, but here we go. So for each pair of opposite parabolics, the following three things should hold. The first thing is that the group K should decompose with respect to M, N, and N. So K should be equal to K intersected N times K intersected M times K intersected N bar. And I want this K intersected M to be just Km. So that means K is really just, so this here is Km. It's just Km, and on both sides you add some unipotent radicals to it. Maybe as reference, note that actually N times M times N bar inside G is open and Zariski dense. So we get almost everything of G by doing that, but not quite all. But we want that we get everything when we do this and intersect it with K. So that's the first condition. The second condition, and you can do actually an exercise and check that this works with this group here. That's why I've created this weird group here, because that group then Gx, this group Kx0 satisfies this property with respect to this compact subgroup of Mx0. So that's why I had to construct this complicated thing here. That's the first part. Well, then we want rho and rho m should be somehow connected. Well, the thing you can guess should be true, essentially. So if I take rho, and restrict it to km, that should be just rho m. And if I take rho and restrict it to any of these two opposite unipotent radical thingies, then I want this to be trivial. Is trivial. So in other words, it's equal to the identity of the underlying vector space. So it's really, something is funny, I would laugh. Okay.
Sorry, it's like if you want to be really annoying about it, they cannot be equal because they are not representations of the same group.
Thank you. Excellent.
But I mean, they are not representations of the same, it doesn't matter.
Now I restrict this to k. That's excellent, that's true. This is isomorphic, and this is isomorphic to the identity as well. Both act trivially, yes. And both are trivial. Thanks. That's true. That's the difference between writing on the blackboard and writing papers. So yeah, rho should be just what you expect. It should be on this middle piece, it should be rho m, and on these two outer pieces, it should be trivial. And the third piece, well, that's slightly technical. What is the third saying? This third one is actually just making everything work eventually. So let's see, how do we formulate this? Let me just see what's the easiest. So for any pi v irreducible representation of G, what we can do is we can construct its Jacquet functor. So the Jacquet functor is a map from V, where we quotient out, we map to V sub n, which is equal to the representation V, where we quotient out everything that's generated by pi n minus n for n small n inside capital N. And what we want is that this map, so for every irreducible representation of G, this map, this Jacquet functor, restricted to the subspace that is rho isotypic, so the subspace which I denote by k, ampere k rho, which is just the subspace, the rho isotypic subspace. How to write this best? Subspace of V on which the action of pi, so the action of pi is via rho, but well, via a bunch of copies of rho. So the rho isotypic part, we want that this restriction is an injection. So restricted to here is an injection. And I totally admit that this is a slightly technical thing. What can I erase? Ideally, I don't want to erase anything. So let me see if I can squeeze something below. So that's now the notion of covers. And here's the theorem by Bushnell and Kutzko from 1998 that says, suppose K rho is a cover of Km rho m, and suppose that Km rho m is an M sigma type in M. So that's a supercuspidal type in M. You can upgrade this to involve a third levy, but I thought for simplicity, let's do this version here. Then K rho is an M sigma type in G. So that means if we want to construct types, M sigma types in G, k rows, what we really have to do, or one way to achieve that is we construct a type km rho m for M sigma, and then find a cover of that. Find a cover k row of that. And that's what we have essentially for JKU's construction. For JKU's construction, we have all these km rho m's, these M sigma types, because that's just the supercuspal case, and as the fact that was written there that I erased from this construction of supercuspal representation, we also obtain the supercuspal types. So that's a supercuspal setting because M is equal to M. And then all we need to do is we need to construct covers, these k rows, that are covers of km and rho m. And that's what Kim and Yu did, and that's how this construction works, and that's why the construction here is so similar to the initial construction. All right. I think I want to leave it as is, like that, for the type theory, and then I want to use this type theory to, I want to, in the second half, tell you about the Hacker algebras that then allow us to use type theory. Are there any questions about the construction of types so far? Then I think we take a 4-minute break and start at 6 past, and then I tell you all about I tell you something about Hacker algebras. I think it's time to continue. So, I promised you to tell you something about Hacker algebras. So, Hacker algebras. A lot of people think about a lot of different things when hearing Hacker algebras. I'm referring to Hacker algebras constructed from types. So, let me just quickly recall the definition. Let's say K inside G is a compact open subgroup and row representation of it. So that's what we use throughout. So K inside G, compact open subgroup, and row is a representation, an irreducible representation of K. And then the Hacker algebra attached to, let me maybe also put G into the notation, attached to this data. These are all the functions from G to the space of endomorphisms, just as complex vector spaces of the space of V rho that satisfy the following two properties. We have that f of k, g, k prime is equal to rho of k, f of g, rho of k prime for all small k and k prime inside capital K and g, small g inside capital G. And we also asked f to be compactly supported. So that's the definition of Hacker algebras that I've given last time. We also observe that, well, I claimed this during the first talk that this Hacker algebra is the same as the space of G endomorphisms of the compact induction from K to G of rho. So there's this tight connection between these two things. And, well, let me just tell you what this map is. If you take some element in the Hacker algebra, what you get is here you need to construct a map, and there's a black box here for a moment. You just take a f, a compactly induced function inside this compact induction, and you send it to the convolution of the two objects. So I still need to define for you what convolution is. So I've just defined for you the space, but it's actually an algebra, so it's an algebra together with the convolution. What's the definition of the convolution? If I take two functions, I guess I called them phi, phi1 and phi2, the convolution of the two, it's again a Hacker algebra, an element of the Hacker algebra if the two are in the Hacker algebra. So I have to tell you what this element is evaluated at G. And that's just the integral of f1 of phi1 of x times phi2 of x inverse G. Now I ran out of space a bit. F compactly supported. dx, where I integrate over the whole group. Instead of integration, well, if I say integrate, it's actually a Haar measure that has measure 1 on K. I could also write this as a sum, so maybe I can just write this down here. That's the same as you just sum over the double cosets of G mod K, and then sum this same thing. Phi 1 of x, phi 2 of x inverse G for x inside this quotient. So that's the convolution that turns the Hacker algebra into a Hacker algebra. So it turns this vector space into an algebra. And this algebra is isomorphic as an algebra to the space of the algebra of endomorphisms with composition. And you can write down an isomorphism rather explicitly. You have to check that that map works. And you can write down an inverse rather explicitly. And so that's what we want to understand now because of the result of Bushnell and Kutzko that actually the Bernstein block is equivalent to modules over that Hacker algebra. All right, so let's see, what do I want to do? Maybe I want to give you some examples first. So just to keep in mind some examples, the easiest example, well, I've given you some examples already in the first lecture, so I'm now upgrading these examples a bit to make things more interesting and complementary. So we can take a group G such that the center of G is finite, and then we can just take a supercuspal representation, so say pi is the compact induction from K to G of rho. Say this is irreducible and hence supercuspal. And in that case, well, the Hacker algebra here is rather boring because the attached Hacker algebra. So first of all, we know that K rho is a type. So we even have a type here in the attached Hacker algebra. Well, that's just isomorphic to the endomorphisms of this compact induction. Since this is irreducible by Schur's lemma, there are no interesting endomorphisms other than scalars. So this is just the complex numbers. That's just C. So that's rather boring. The second example is maybe a bit more interesting. So that's the example where let me take G to be just the multiplicative group. So explicitly, the QP points would be the invertible elements inside there. I can take as my compact open subgroup just what I would call GX0. So this is just the invertible elements in ZP. And then if I construct the Hacker algebra for a representation, so I need a representation, say rho is just the trivial representation on the one-dimensional vector space. Then by definition, the Hacker algebra attached to this triple, these are all the functions from G that from QP star to the endomorphism of this vector space. So that's just C that transform on the left and the right via the trivial representation here. So in other words, it's just functions on the quotient with CP star. I have to take the quotient on both sides, but since everything is abelian, there's not much I have to do on both sides. One side is enough, and F is compactly supported. What is this quotient? Well, this quotient is just isomorphic to the integers Z, so n could just be sent to p to the n. That's our isomorphism. So really, what is this Hacker algebra? This Hacker algebra, it's just functions from Z to from the integers to C that are compactly supported, of course, supported only on finitely many of the integers. So in other words, that's just a priori as a vector space, just the group algebra over Z, but you can check that this is actually, as an algebra, isomorphic to the group algebra over Z. So that's some exercise that you can check that the convolution here actually translates into the multiplication in the group algebra. So that's a nice example. Last example, let's say G, maybe for simplicity, is split. And I take X, the point in the building that is in the interior of a chamber, so of a maximal facet. So X should be inside C, where C is a facet of maximal dimension. So for example, for G being SA2, I can take my We're at Tietz building, the infinite tree, and I can take x somewhere on this facet. So this would be my chamber C, and I take a point x in there. And then as my compact open subgroup, I can take Gx0, which is also known as the Iwahori subgroup. So in this example here, K would be just the matrices with ZP on the diagonal and PZP in the lower left corner and ZP in the upper right corner. And as my row, I can take again the trivial representation on the one-dimensional vector space. And then we can try to do the same thing. We can try to construct the Hacker algebra attached to this information, to this input. And so as before, these are functions that transform trivially under K. So these are now functions on G, where we mod out on both sides by Gx0 to, well, again, it's just C, and that are compactly supported. Compactly supported functions. Before, it was rather easy to understand what this thing here is. In that setting, well, it's actually not too difficult, but maybe let me make one assumption to do that. Let's see, what did I? Well, let me maybe just say that first. So one can actually check, let's say fact, that this is the same as a double coset. You have an isomorphism between the single, also double single coset, the normalizer of the torus mod out by the zeroth filtration subgroup of the torus. So the maximal compact subgroup in the torus where T is the maximal split torus of G. And this was just the double coset. This is now actually a group. This has a much nicer structure. So this is a group. And let's just call it W tilde. Sometimes it's called W tilde. It's an extension of an affine Wall group. And so what is the Hacker algebra? Well, the Hacker algebra now is functions from this quotient to C, but then we need to understand what this weird convolution is. And previously it turned out to just be the group algebra, but here it's not just the group algebra. So here the convolution is more complicated. And so here's how it goes. So let's, just to make my life easier, suppose that G is semi-simple. So the center is finite and simply connected. Simply connected. So these two things actually just mean that the stabilizer of my facet C is the same as the pointwise fixator of the facet. So that's what I want to assume to just make my life a bit easier. So then it actually turns out that what is this group? This group here, this quotient, which is indexing our functions, the support of the functions, this group is an affine Wall group, and it's the affine Wall group generated by the reflections across the walls of my chamber C. So in the example for SL2, we just look at one apartment. These are the walls. That's my chamber C. And then it would be just the group that's generated by S0 and S2, the reflections across this wall and that wall. So it's two generators. In that case, and the only relations are that these are reflections, so that their square is 1. In the case of SL3, the picture looks a bit more interesting. The apartment, you've seen this at some point. Let's see. It's always a bit tricky on the blackboard. That's how the apartment looks like. In that case, my fundamental chamber could be, for example, this, could be C. And then the reflections would be across the three walls here. So one reflection would be across that wall, another one would be across this wall, and the third one across that wall. And you see in that case there are a bit more relations that come up. So that's actually W tilde, so it's something very explicit. We also often write this then as WF for affine, the affine Weyl group. And in that case, we can describe the relations very explicitly. So the Hecke algebra, now as a vector space, it's just the direct sum of C's of complex numbers, one for every element in our affine Weyl group. Let me give these generators a name. Let's call them TW. So that's just as a vector space. It's just, this is the indexing set from where we map to C, so that's just another way of writing that. And all I need to tell you is what are the relations, because the relations are no longer just the group algebra. So with relations generated by two types of relations. The first relation is that for each of these generators, so let me give them a name. So the affine Weyl group is generated by these reflections across the wall, and let's call this set S. So in this example here, S would be S0, S1, S3, S2. Sorry, it should have been 2. I can't even count 0, 1, 2 rather than 0, 1, 3. And so for each of these, we have a relation, which is that if we take Ts and multiply it with Ts, what we get is Q minus 1 times Ts plus Q times T1. For what is Q? Q is the cardinality of the residue field. Cardinality of the residue field of our local field F. I think we called this earlier also FQ already. So it's just the number of elements inside FQ. And S are all these generating elements of our affine Weyl groups. For all these generators, well, inside the affine Weyl group, we know that the square of these elements is equal to 1, because these are just reflections. Here, the square is not quite equal to 1. There's some error term here. So that's one condition that we have. And the other thing is that if we now take an arbitrary W, then we can write W as S1 times S2 times Sn, where Si are some element inside S, and this should be a reduced expression. Reduced expression, meaning a shortest way of writing W as reflections. And then the corresponding T sub W is just given as Ts1 times Ts2 times, and so on, times Tsn. So we build everything else out of that by just multiplying things. But we have these interesting quadratic relations here. The second one also gives us interesting relations, because if there are two ways to write W by a reduced expression, you require these two expressions then to be the same. And that's the standard Iwahori-Hecke algebra that people work with. So that's also called an Iwahori-Hecke algebra. And that appears throughout mathematics. A lot of people are interested in this object for various different reasons. And so now we have seen three important examples. We have seen the trivial case and the Super-Caspel case. We have seen the group algebra case that can occur, for example, if we just care about the center. And we have seen the other extreme, which is this Iwahori-Hecke algebra. And so what I want to tell you now, show you, is that general Hecke algebras look like all these three together. It's a bit like JKU's construction was. We take the def0 construction and we take the character construction and put it together. Now we put these things together. It's not quite for the same reason, but a bit. So that's what we want to do. Any questions so far? So before we do that, let me actually just recall the theorem from last time, quickly by Büchner and Kutzke. That was the whole motivation for doing this, which is that if K rho is an M sigma type, then the Bernstein block attached to M sigma, so everything that we obtain by parabolically inducing this M and sigma and then taking everything that has some interesting extensions with it, this was isomorphic to the modules over the Hecke algebra attached to the type. And by modules, I mean right unital modules of this Hecke algebra. So that's something I wrote already down in the first lecture. That's the motivation for why we needed types to begin with. We need types, and why we want to study the Hecke algebra. And I wanted to just give you an idea, how does this actually, where is this coming from? It's not just like in the first lecture I just said that's magic, here it is. But it's actually rather explicit. If we take some representation inside this block, how do we get the module out of that? Well, it's a type, so I think I recalled over somewhere, I recalled what types are. Oh no, it's gone because maybe it was last time. Type meant that we had some interesting non-trivial map between rho and pi restricted to K. So the space of K homomorphisms was non-trivial. So that's what it meant to be a type. And now we can just view this as a module over here. But how on earth do we view this as a module? Well, you can write down this very explicitly, but you can also write down this abstractly and see it easily. One can use the Frobenius reciprocity to see that this is the same as the G homomorphisms of the compact inductions from rho into pi. That's just Frobenius reciprocity. And now we can just precompose such a homomorphism by an endomorphism of the compact induction of rho. So sorry, I should specify K to G, K to G. And this is just, as you've seen over there, this is just the Hecke algebra. So that's how, starting with the representation, we do get our Hecke algebra module just by homing into our representation via this compact induction and then precomposing with the endomorphisms of this compact induction. So it's rather explicit, even though it might look a bit miraculous on the first time you see this isomorphism. Here it is, it's rather explicit. All right, and that's what we now want to use to actually understand the Bernstein blocks by understanding the Hecke algebra. So that's our motivation. So from now on, or do I want to, let me double check, do I want to do this now? No, I want to make one more statement and then I make this assumption that we're in the commute setting. So the first statement I don't need it for. First I want to tell you what the support is of the Hecke algebra. So the support, for this I don't need the assumptions yet. I want to understand the support of the Hecke algebra. If I need to understand the Hecke algebra, well, I first need to understand the support of the Hecke algebra and then need to understand what happens on there. So what is the support? By the support, I just mean all the elements in my group such that there exists some function in the Hecke algebra such that this function is non-trivial on the element G. So all these G's where something is non-trivial on. And so here's my claim. My claim is that we can understand this support rather explicitly. And the claim is that the support of this Hecke algebra is equal to all the elements inside G such that small g intertwines K rho. So you see this notion of intertwining comes up over and over again. Let me maybe also just call this the intertwiner of k and rho. So that's my claim. Let me see if I have time to prove it. Yes, I think I have time to prove it. Okay, now that's really unfortunate. Let me keep the definition of the Hacker algebra. So that's our definition. So that's my claim. Here's the proof of the claim. So what inclusion do I want to show? I want to show first the inclusion that if something is in the support, then it's also in the intertwiner. Is that I always get the inclusions the wrong way around. No, that's the correct inclusion. Excellent. So what do I need to do? Let's take a function in our Hacker algebra, and let's take an element g such that the function on g is non-trivial. And now I want to actually show for you that this means that the element g lies in the space of the intertwiners. So what does it mean to be an intertwiner? It meant that there should be a non-trivial homomorphism between g rho, the g twist of rho, and rho. And my claim is that actually phi of rho is doing that. So let's take some element k inside the intersection of gk with k. And let's just see what happens if we apply rho of k first, or second, sorry. If we first take that and then phi of g, so in other words, we first apply phi and then rho. Well, by the very definition, I've written this down here again, up there. This is just phi of k of g. That's just the definition of phi being an element of H. Now, I can just rewrite this as g inverse k, g. I just added 1 here, nothing fancy. Now, what is this thing contained in? Well, this thing is contained in g inverse g and whatever k is contained in. Small k is contained in this intersection. So in particular, it's contained in the g conjugate of capital K. What is this? Well, I conjugate k by g and conjugate back, so this thing is just k. So this element is contained in k by my choice of small k being in this intersection. And now I can apply the property of the Hacker algebra that it transforms on the right via rho. So now that's equal to phi of g times rho of g inverse kg. But what is this rho of g inverse kg? This is just, by definition, the g twist of rho of k. So that means that this rho of g here actually is a homomorphism between these two spaces. So in other words, phi of g is a homomorphism between rho of, I'm mixing up things, between g of rho, the g twist of rho, and rho as a representation of k intersected gk, as a representation of this group. Well, but that's by definition just saying that g lies inside the intertwiner of k rho. Because g lying inside the intertwiner means that this space is non-trivial, and we found something non-trivial in this space. So that's the inclusion in one direction. The inclusion in the other direction, let me just say exercise. You just construct it explicitly using exactly that. All right, so that was just a general observation about the support. That also shows you how all these things fit together. And now I will want to specialize to the setting of the Kim U types from before. So from now on, I want to work with Kim U datum. So now, from now on, fix the Kim U datum. So the datum that I had written on this side earlier. And from this, we obtain this representation k and rho. And we also obtain the representation k0x rho 0. Maybe I can put here an x as well if I want to make clear which point I'm working with. So that's what we constructed thanks to the construction of Kim and Yu. So this rho here was rho 0 tensor kappa, where kappa includes the epsilon twist. And this rho 0, this is the depth 0. That was the depth 0 input. Depth 0 input. So this kx0, let me recall for you, that was this g0 x0 times m0x, and you take the maximal compact subgroup of that. So that was the input we took to construct the other things. All right, so that's the setting we are at now. And what can we do with that? So here's a nice fact. So we really want to understand the support of the Hecke algebras now. We want to understand the Hecke algebra for this type and for that type, and the final result will be that they are the same, or isomorphic. So we want to first understand what the support is, and the support we know is the space of intertwiners. So here's the nice fact. If you look at the space of intertwiners of kx and rho, this is a kx double coset. So this is something kx, something else kx, simply because kx intertwines rho. So you can add that on either side. And it turns out that this is just the same as the intertwiner of kx0, rho 0. So the two intertwiners, all the elements that intertwine the smaller thing and the elements that intertwine the larger thing are the same, up to, of course, the intertwiner here lies inside G0, while the intertwiner of the bigger thing lies inside G. How do you prove that thing, actually? Well, you prove it the same way as I outlined earlier for you the proof of supercuspidality, this step 1, step 2. That's exactly the same proof here. Well, up to minor details, but that's how you prove something. So basically what we did when we tried to prove supercuspidality is we tried to show that the intertwiner of something is just k. And here now, the intertwiner will be larger because we don't get supercuspidals, we don't get irreducibles when inducing, but it's something, and the nice thing is this relation between these two things. So that means, in particular, this means that the support of the Hecke algebra for k, or kx, and rho is the same as the support of the Hecke algebra for G0, K0x, and rho 0, up to, of course, noticing that these are two different double cosets. Which also means one can, which in particular means that the Hecke algebras, they are as vector spaces. As vector space. This is a bit lame because they're just infinite dimensional vector space, but as vector space, it's just the sum of complex numbers over the support. So over the support modulo the compact open subgroup. And so that's just the same for the two. So as vector space, we know that the two are the same. And what we really care about is what happens now with the algebra structure. All right. So ready for the final bit. So I've now introduced for you abstractly what the definitions are and all these things, and now I want to tell you the results that are actually saying it's not just an algebra, it's not just a vector space isomorphism, it's an algebra isomorphism, and we understand the structure. So that I'll do as a 3-part So first, small proposition to understand better what this support is. So all the three results now are joined with Jeff Adler, Manish Mishra, and Kazuma O'Hara, and all of that is in progress. So the first result is saying that we actually understand this support better than just saying it is this weird thing here. So the first result is saying there exists a subgroup which I call N heart. And I can actually write down the subgroup explicitly for you if you're interested, and I would just have to write down a bit more notation beforehand. It's a subgroup of the normalizer in G0 of, what do I want to normalize? I want to normalize M0. I want to normalize my group M0. And I also want to normalize this compact subgroup of M0 that we care about. So this is the normalizer of these two things. And my claim is that there exists a nice subgroup inside there that has the following property. So such that if I look at the support, well, what is the support? The support, say, let me take the bigger one. It's the kx. This is the intertwiner of kx rho. But if we really want to care about an indexing set for the support, we have to mod out by kx on both sides, because the functions transform via rho on both sides. So this is really the indexing set. Then the claim is that this is isomorphic, well, as a set to this normalizer, mod out as the subgroup of the normalizer, mod out the intersection with mx0, the compact open subgroup inside there. And this thing here is actually a group. Well, it's a group mod out by a normal subgroup. It's a group, so that means we can actually give the support a group structure. And this group, let's give it a name. Let's call this maybe W heart. So this is very similar to what we have seen before in the two examples. The group in one example was the integers, in the other example it was the affine Weil group. All right, here we have the support. Why did I actually, this might look a bit abstract. It is nice, it's a group, but I really just wrote this down so that I can write down the main two theorems. Let's maybe call this theorem 1. It's the same people in progress. So let me now abbreviate all our names by AFMO, which is telling us how we get a Hecker algebra isomorphism. So here's the result. So there exists representation kappa tilde. What is a representation of? A representation of this group and heart times mx0 compact, so that times the compact subgroup in M. And this is a representation. Well, a representation means it goes to some endomorphism of some vector space. It should go to the endomorphism of the vector space of kappa. So it's actually just an extension of kappa. So there exists a representation kappa tilde such that if I restrict kappa tilde to this subgroup M0x compact, so this compact subgroup of mx0, then this is just giving me back kappa. Let's see, I actually, that is true, but I actually want to not just go to M0, but I want to go to the whole thing. So let me extend this slightly larger because that's what I need. it's a representation of this times the intersection of all of kx with m. It didn't quite make sense to just look at mx0. So that if I intersect with g0, I would get this back. But I really want to go to all of m. And if I now restrict this to kx intersected with m, this is just kappa, maybe equal. I want to really extend it. So I take kappa. Kappa is a representation that we constructed earlier. It was a representation of this kx, because that's where we really constructed it. Because kappa was, so let's recall that we had rho being rho 0 times kappa. So kappa was this representation of kx that we constructed from the characters phi and the epsilon. So this kappa here was really this non-twisted kappa that were attached to all these phi i's, tensor with the epsilon, this plus minus 1. So that was kappa. And now I take my kappa on kx. I restrict it to m, because that's, for technical reasons, need to restrict it to m. And now I claim that this kappa, so this is also really kappa restricted to kx intersected with m, I can extend this kappa to a representation of this huge other group here, the subgroup of the normalizer. So I extend this kappa tilde to a representation of a much bigger group.
Is this product a group?
Yes, this product should be a group. This is this should be normalized. Yeah. Yeah. Thank you. And that's actually why I need to take the intersection here, because that doesn't make sense. That's not really a group, and it doesn't work that way. That's why if I intersect with m, since this is a subgroup here that normalizes m0, but also then m, and that's why things work out nicely, yes. Thank you, excellent question. And so that's actually the very technical part of this result, to construct this kappa explicitly, because it involves actually extending this epsilon twist to a larger group, and that's not so easy. All right, so the claim now, what is the theorem? I didn't get to the theorem yet. I started with the technical part. So the theorem is there exists this lift of kappa, and such that we actually, or maybe I shouldn't write this again, just say and. So such that this holds and, such that we actually get an isomorphism of Hecker algebra. So we get an isomorphism, let me call it I for isomorphism, between the Hecker algebra attached to rho 0 and the Hecker algebra attached to k and rho. And that's not just an arbitrary isomorphism, but this I can now explicitly describe for you, such that this holds, and this is an isomorphism defined by the following. And now I want to define this isomorphism explicitly for you. In order to do so, I need to erase something. What do I need to erase? I need to erase that actually the blocks are equivalent to modules over the Hecker algebra. So let me first, before erasing, say, as a consequence of this result, we obtain an isomorphism of Bernstein blocks. All right. Here comes the explicit version of the isomorphism for you. So defined by the following. Let me put colon. If we take an element inside this depth 0 Hecker algebra and say that the support of phi is just, well, we know that the supports are multiple sums of unions of cosets. So let's say it's just the coset corresponding to one element n. Is this coset with n being inside n hard? So we know that the support is indexed by quotients of n hard, so we can actually find, well, if we take an arbitrary element in the Hecker algebra, we can write it as sums over elements each supported on a single double coset, and each single double coset is of this shape with n contained in n hard. That's why I needed the proposition. And if we take such a thing, then I want to describe to you what I of phi is. And this is now an element of the Hecke algebra for k and rho. And this thing has support in kx and kx. So the map is support preserving. We preserve the support. So far not so interesting. The interesting part is what is actually the thing. So what is this object? So if it has the support in this double coset, in order to describe it to you, I just have to tell you what happens if I evaluate it at n, because everything else you can deduce from it. And, well, what is this? What do we need? So this has to be an element of the endomorphisms of V rho by definition, over their definition. And what is V rho? V rho is V rho 0 tensor with V kappa. And so I need to give you now an endomorphism of this space. And, well, I give you just an endomorphism of V of rho 0 is just given by phi of n. And then I just tensor this with an endomorphism of V of kappa, which is just like kappa tilde n, which is just this extension here. And then, well, for some technical reason, which is actually just coming from the definition of convolution, I need to add in a scalar. And this is, what is this? This is just some scalar, which is you take the group K0 and look at the index of n, the n conjugate of it inside this subgroup. And then you do the same for K. And then you take the quotient and the square root. And this is just a constant that comes up in the convolution. So it's actually nothing bad. And that's it. That's the isomorphism. That's the isomorphism. All right. While you digest this, I make a bit space. What was the question? Sorry? Yeah, that should. I think that's a power of p. Is it a power of p? Yes, it's a power of p. I think it should be a power of p. Yeah.
The restriction of kappa to kx intersect n, is it still irreducible?
Yes, that is still irreducible. That's a good question. This is still the Bay-Heisenberg representation, essentially. Yeah. All right. So that is one big result. It's how we can relate everything back down to depth 0. Now people might be interested in, okay, now I'm telling you that something we don't know is isomorphic to something else we don't know. So the final theorem will be telling you a bit about the structure, telling you that we actually know the structure of that. So that's the same authors in progress. Which is just saying that, well, what is we know that the support is this group W hard. And it turns out that we can write this W hard as a semi-direct product of one group that I call omega and another group that I call W of rho. I just indicate the rho because that's what's really underlying the whole thing. F, which is, this is an affine Weyl group. So in the examples before, so in the examples that I had earlier, in the example B, our W hard was just equal to the integers, and that was just this omega rho here. So in that case, the affine Weyl group was trivial. And then the second example that I've shown you, the omega hard, was this affine Weyl group. And in that case, the omega is the trivial part, while the affine Weyl group part is just this affine Weyl group part. So these are the two examples that I've shown you earlier. So the Z example was this omega, and the affine Weyl group example was this affine Weyl group. And in general, we just have to put things somehow together. All right, so what do I want to say? I want to say once we have this decomposition, or we can find such a decomposition in such a way that the Hecke algebra is actually isomorphic to an analogous semi-direct product of a group algebra of this omega of rho, but twisted by some cocycle mu. So where mu from omega rho times omega rho to C is a 2 cocycle. So cocycle that twists the group action. So the group action is just twisted by that. Semi-direct product with the affine Hecke algebra of this second group for some parameters Qs. And what are Qs? So Qs are elements of the rational numbers that are greater than 1. So they are all, none of them is equal to 1. And well, 1 for each S inside capital S, which is a generating set for the affine Weyl group. So it's like the same S that we have seen before, such a generating set. And this Q, what is this affine Hecke algebra? Well, it's the same thing as in the example I've shown you before. And we had this quadratic relation where back then we had a Q in there, which was the residue field characteristic. Now Q is something different. For each generator, something else. One can describe this rather explicitly. But that's what it is. What do I know about the omega of rho? It is whatever you need, such that W. I don't know what kind of. So the question is, what is omega rho type of a group? And I can't give a good answer. It is really the thing that. So I can really describe this very explicitly here. It takes a lot of time. And omega rho is then the complement. So it can. So if you just work with the Iwahori Hecke algebra, then this rho would be just the stabilizer of your chamber. So I simplify to the case where the stabilizer of the chamber is the same as the fixator, the pointwise fixator of the chamber. And if you were to not make the simplification but work with general G, then this rho, this omega of rho would be just the stabilizer of this chamber. In general, this affine Weyl group is not the affine Weyl group of the affine root system of the group G, but of a different affine root system. And again, this omega of rho is a stabilizer of a chamber in this affine root system. But it's more complicated to describe this affine root system. It's more complicated to describe this W hard, but that's again, it's just the stabilizer of this chamber. What it can be, do you see, it can be Z, so it can be infinite. So I don't actually know what possibilities can show up here. It's a more complicated question. Yeah. All right, let's see, do I want to say anything else? Well, I can say more about everything if you want to, but let me maybe just give you, this is like the final picture. So we have now the statement that these Hecke algebras are isomorphic, the arbitrary ones are isomorphic to depth 0, everything can be reduced to depth 0, and all these Hecke algebras have this particularly nice form, where it's a group algebra twisted by a 2 cocycle times this affine Weyl group. If you're interested in any details, I can explain more, but I think, let me just stop here for this lecture series, so you can ask me after, or you can in a moment, more questions, And let me also thank the Collège de France very much for this invitation. It was really a pleasure to be here, and thank you also to everyone who is coming to this, and thank you also to my colleagues in Paris who have been very nice and welcoming to me. Thank you.